In Lab Exercise 5, we will pulse the voltage applied to the wheels to slow them down. We'll use the pre-lab as an opportunity to build a pulsed or square wave voltage signal called an oscillator. In lab, we'll speed the rate or frequency of pulsing to where our human senses can no longer evaluate the oscillator. We'll need the oscilloscope to gather numeric data about the pulse signal, always starting the oscilloscope in the default setting. We'll compare two identical circuits independently constructed, using the oscilloscope to see if they can be made to operate at exactly the same rate. Triggering on channel 1, it becomes clear that the circuit on channel 2 marches to its own drum. But what if we tune one of the oscillators by using an adjustable feedback resistance? Can you get the frequencies to match and get two static traces on the scope? Now let's return to our car. Perhaps we can slow the car by pulsing the voltage that controls each motor drive circuit. Let's remove the high end of the potentiometer from the power rail and instead bring them together so we can drive them with a square wave signal from the function generator. With an offset, amplitude, and frequency matched to your oscillator, change the duty cycle between 20 and 80% and observe its effect on the car wheel speed. Now transfer an oscillator onto your car's breadboard to replace the function generator. Although far from being an ideal method, the wheel speed can still be controlled by tuning the individual potentiometers for each wheel. You will need to set your car on the floor as you tune to verify that the car will travel in a straight line. Again, the oscilloscope provides a window into the operation of your circuit. Since each black wire of your oscilloscope probes are internally connected within the scope, you must be careful that multiple scope channels connect the black wires to the same node on your circuit. Now we can observe the voltage at the gate of each MOSFET, the voltage that drives each wheel. In fact, the signal is unchanged if the two black banana plugs are combined and only a single alligator clip connects them to your circuit. To measure across each motor simultaneously, we'll need to connect both black probes to the power rail, since the opposite sides of the motor do not share a common node. You may be surprised to see that not only is the voltage across the motor not a square wave, but its maximum voltage exceeds that of the battery. This occurs because of the complex electromagnetic behavior of the motor, where it cannot be modeled as a simple ohmic device. We can actually clean up this signal and protect the motor's windings from damaging effects of high voltage spikes by adding a diode in parallel with the motor. On the right, we have a motor with no back EMF diode protection displayed on channel 2, and on the left, a motor with a diode across it. The addition of the diode leads to a much cleaner square wave signal. Again, work on modules as time allows, play with your car to identify the strengths and weaknesses of this design, and answer your lab summary in your breakout session. Don't forget to clean up your bench and return your batteries and cables so that you don't lose points. Next week we'll make a closer examination of the models we use for batteries and motors.